Hello and welcome to Ubiton AI Labs. I'm Sándor, this is episode 2, and today I wanted to continue with the variational autoencoders. However, I decided let's have some fun with the normal autoencoders, and today we are going to build this, a Morphing Faces GIF. And we are going to use a custom dataset from Hugging Face and our notebook from the previous episode. If you don't have this notebook, you can download it from the Skool Community. It's free, you join and download. And let's get to it. So last time we used the Cypher10 dataset using Torch version and its built-in libraries. But today let's swap this out in favor of a Hugging Face dataset. So basically you will be able to pick any dataset you want as long as it's on Hugging Face or similar platforms, which is in itself much more fun than using pre-built benchmark databases for researchers. So let's just get rid of these two lines, and we need to install the datasets library with, I think, hfset utility library. For me, it's already installed, so that's fine. And from the datasets, we'll import dataset and load dataset. We'll move our transform outside. And for this example, I generated a new dataset. It's under my username. And I found a Faces dataset that contains 1024 by 1024 images, but it's huge for just training a toy example neural network, so this is much faster. You can find it in 32 pixels and 256 variants as well. It will download the dataset into the cache there. And actually, I have saved the script. I will share this also in the Skool community. We are not going to go through it in detail, but basically it pulls a dataset from Hugging Face that has only images or an image column. If you pull a different dataset and the column name is different, then of course you should rewrite this. It saves it to this directory. Actually, it saves it to its own directory, so if you want to set cache dir here, that's fine. The save directory is for the output, because this script pulls the dataset in this size, and you can set the target size, in this case 256. So it will just resize all the images, save it to a folder, and then you manually need to navigate into that folder, and I'm going to leave a comment here. Create a train test folders and decide your split. For example, you allocate 5,000 images for training, then copy the first 5,000 images into the train folder and copy the rest into the test folder. Now when you're done with that, here it loads the data set from your folder. Well, in this case it's faces, whatever. You can set that here to whichever directory you like on your local machine. Now for some reason it automatically added a label column for me, so I just removed that. It will print out here like here's the train data set with image and label, the number of examples in both. Then I removed the label, verified it works, and you can push it into your own Hugging Face account. Here your Hugging Face username and whatever commit message, describe it nicely. And don't forget that you have to create a .env file just right next to this notebook and put and put an HF token variable in it. This token you can generate on Hugging Face, and be cautious, do not share it with anyone. So load.env will load this token, and then you can access the hub and push this data set. From then on, you can use it in your own examples just like me. So if you prefer pictures of, I don't know, UFOs, then you can use that as well. In any size, basically. So if you have a stronger machine, you can even go up to 1000 by 1000 or 16 by 16 if you're just playing around with a C64. So we have our data set, but we can't use it just like that because it's a bit different. It has a bit different interface. So we have to have a transform function declared outside here. I have a ready-made notebook, so I'm peeking on the left because I'm checking what's next. So basically, this data set has an image column. It's in a columnar arrow database, in an Apache arrow database. So that's why the field here is image. If your data set has a different field, then obviously this will be different as well. And this is going to be the transformation for the input images. Now originally I just used the huge 1000 by 1000 images, and I was like, okay, let's just use that, and we can do t.resize. But actually that turned out to be very slow, because the transformations don't run here on init. They run one by one when the images are pulled from the data loader during training. So it doesn't just train the model, it also resizes the images, so the training took like forever. So that's why I went ahead and made this script. So you can resize your images and it's gonna be very fast for training. So currently it's just 2 tensor here, but obviously you can apply random horizontal flips and whatever other transformations. I leave it up to you to experiment, but this works. So this data set has a train and a test split, and we are going to remove the persistent workers and the num workers from here. I couldn't get it to work with these parameters. For some reason it always threw an error, so you can try. If you can get it to work, then cool, but otherwise I didn't really notice a downside in this case on my machine. So let's create these. So these data loaders should work. The batch size is 64, we can keep that as well. No shuffling for the test data set. And because in later stages I was referring to Cypher10, let's just return the data sets themselves here as well. So that's gonna be ds train. But remember, this is a columnar database and it has an image column. So I'm going to return it like that. And then we don't need to otherwise we would need to refer it like this. But now you can access any training example as it's here. Okay, so let's see what we have in this data set. Yeah, let's take as an example image 1200 and just show it with matplotlib. Now remember, we have to permute the access to be compatible with matplotlib. Turn access off, plt.show. That should work. Or maybe not. Let's see. Yeah, I'm used to Axios. It's just access. So, it's a face of a woman. Another example. Beautiful woman. All right. So, we have our data set. You can use now anything from Hugging Face, really. And we have our previous encoder and decoder modules. And our previous example was a 32 by 32 image. This is going to be larger, 128. So because of that, we also need to change the architecture of the model because the sizes are different and this linear layer, it won't be 4 by 4 by 256. It's gonna be first 64 by 64, then 32, and 16. And for this size, let's just add another layer. So in the end, it will be an 8 by 8 image. Now you can notice that our network is growing and we have lots of repetitions. Later we will need to add more layers, and these are so-called blocks. So to avoid the repetition that we are facing here, we can declare our own function. I will talk about dropout a bit later. For now, let's just pass this here. Kernel size is 3. It's always 3 because we downsample in every block, so we don't need to parameterize the kernel size, the stride, and the padding. However, the input channels are different, and the output channels are different too. We have a nice ReLU nonlinearity, and with this we can easily create our blocks. Now I'm not going to manually assign a dropout number, but let's propagate that parameter here and set it to, for example, 0, 2. So this was the first layer or block. And now we mimic this one. So the input channels are 64, output channels are 128. Another encoder block with 128, 128. That's done. I'm gonna keep it 128 because actually we don't need that much. It won't really make the model better in so many ways. And the last one, I think we can still keep it at 128. Or if you want, you can also lower it to 64. So it goes as 3 to 64, keeps it at 64, then makes more kernels channels to 128, keeps it at 128. We flatten it. So comment it here. Becomes initially 128, then 64, 32, 16, and 8 by 8, of course. So we have an 8 by 8 image, and for each pixel we could assign 128 neurons. It's pretty big. Let's just try with 64 neurons. Or actually, we can't move because that is the input. So if we have 128 channels here, the image is 8 by 8, we are fixed here. These are those two numbers. The latent dimension is the output. So this maps from 8 by 8, 128 to our latent space. And one more tiny fix, because we are returning an array here. Spread it. Run. Syntactically correct. That's a step. So we can pretty much do the same here for the decoder. So here we project from latent dim. It should be the same if we want to mirror our encoder in the decoder. It's not necessarily, doesn't necessarily need to be the same, but just to have the decoder the same size as the encoder. So that's 128 channels, 8 height, 8 width, the unflattened size. And our decoder block, similarly, going to be in channel, out channel, dropout is just hanging there for now. Let's replace our blocks. But again, we have another layer in the encoder, so we will add another more here. So the input channels are, it's 128. Output channels In the encoder we are keeping it 128, so let's do that here too. Assign the dropout as well. Then it's 128 to 64. 64 to 64. And here we are doing 64 to 3. But realize we are using a sigmoid in the last layer. And since we will use other layers inside the block, I will just keep it as is. So we don't need the last block here. Double check. That's a transpose of this. This block is a transpose of this. This stack block is a transpose of this. This comp transpose is basically the transpose of this. So here we upsample to 60 by 16, 16 by 16. That's 32 by 32, 64 by 64, and that's the original size. Now here, let's test if we implemented these encoder and decoder blocks right. As I said, we don't need to refer to the Cypher10 anymore because we loaded our loaders and sets, so we can address data loaders test ds like this. It's this one that we returned. And if we did everything right, then this shouldn't throw an error. Except the test des now, because Cypher10 had image label pairs, this one only has images. So there's no reason to try to extract it to a tuple. And yeah, it works. So we get back the original image size, apparently, or maybe not. Look here. It's image decoded is the third print. So yes, we do. Okay, this was play with convolution in the last episode. We don't need it now. We have our autoencoder. Now we will introduce dropout later, but it has initial values both for the encoder and the decoder. So I'm not going to pass that here just yet. And you might notice that we didn't talk about the structural similarity index measure in the last video, and this is because for me on these data sets it didn't yield much better results, probably for higher resolution images, but it's just too complicated for basically no gains in this case. So at the end of the last video, this would be the SSIM loss, but our loss was just a simple MSE loss. Lighting wipe, red Y, yes. And we don't have F imported, so let's import F from torch.nn.functional as F. Our latent dimension was 384, but remember it was for much smaller images, 1/4 of the size. So I think it's safe to say we can bump it up to like 512. Or you can leave it like this as well and experiment how it changes the reconstructed image quality if you tweak it. we had 100 epochs with this learning rate. And model evaluation. Now something changes here because our dataset has this image field. We could kind of remove that in this dataset, but when the data loader loads the samples from the dataset, it will not remove it. So both for the evaluation, we need first to remove this because it only returns an image and no label. And so here we use detach, which didn't make so much sense because it's the input. Now we can use clone, and X is going to be X image. In the same way here, when we are training, remove the tuple extraction and just use clone for the output. Then we have our model. It returns the latent and the prediction, the reconstruction basically, and we calculate the losses. In fact, this throws a warning, and the proper use of detach is at this place. So basically, let's try running this. I hope you didn't make that typo. We have a 9 million parameter model. And it will train a bit slower, obviously. So while this is training, here we had our cat. Now we already imported matplotlib in the beginning of the notebook, and test.ts is well, it's declared, but for clarity, let's redeclare it here. That's data loaders, test.ts. Again, it's not a tuple, just an image. And the test here, it consists of around 1700 images, so we can't use this index. Let's address something. So the initial loss was 0.06. So it converged already a great deal, but I expect it to overtrain a bit. Okay, fast forward a bit, training finished, and we can see that our model is overfitting. The average training loss is much smaller than the average evaluation loss, meaning our model doesn't generalize enough, and it won't perform as best with new examples as it performs with the training examples. Let's make a recording of this and see if we can make it a wee bit better. So a standard method to improve the generalization capabilities of models is to use a dropout layer. That's why we set the dropout parameter previously. So dropout layer expects a p probability, and as you can see, let's pass our parameter here. What this does is it per batch, so we are training in batches. This X is a batch of images passed to the model, and for each batch this randomly zeroes out the activations, in this case of this ReLU, with a probability of this dropout value. So this means, for example, you have 1,000 neurons in this layer. Then, if you say dropout 0.4, this means that approximately 40% of the activations will be set to 0. Now, in order to keep the activation magnitude the same, the remaining activations are scaled up. And that's important because the expected value of these activations, the magnitude needs to stay around the same. Otherwise, the layers in the neurons in the next layers would receive smaller activations during training than in evaluation. So intuitively, I think of this as using, when you have a large piece or a large bunch of neurons connected together and they perform some computation and they are too smart for a certain task. You can take a sub-network of all these neurons while the others are at rest and make the model, make this sub-network learn that specific thing because the other neurons are not needed. But this happens randomly per batch. So it kind of generalizes over these subnetworks in a way. And it's fine for the encoder, but the decoder usually utilizes much less of the dropout. So let's put it here. And it's important to put it after the activations. So after ReLU, sigmoid, whatever you have. But generally, it's not a good practice to use huge dropouts in the decoder block. I'm not exactly sure why, but you can look up research articles on this if you want to get deeper into it. So let's rerun our encoder code. And our dropout here is by default 0.2. Let's leave this at 0. You might want to try to tweak it a little bit if you want. I'm going to leave it at 0 for now. This should work as the same. And now we can also leave this as the same. And I save the previous result. So let's see how dropout changed the training. So I let that second training loop run, and now it's here. I set the dropout to 0.2, same number of parameters, and another training is running. We will see how it performs. And as you can see, the end result without dropout on the evaluation set is actually worse with the dropout. However, you can see that the gap between the training loss and the evaluation loss is narrowing. It means that our model is generalizing better now. So there are a few options. There are a few hyperparameters that we can tune. Either run this more epochs, for example 200, 300, even 1000, and maybe it will converge just fine. Now another optimization that I'm trying, because the dropout needed to be set to a pretty large number in case I upped it to 0.3 from 0.2. It means this will disable 30% of the network in all these blocks. So that just means that our network is pretty too big for such a simple task. So more neurons, a larger network, doesn't equate to better results. If you want to memorize some training samples, then that's fine, but it won't be useful in real life if it's faced with new examples. So an additional change I made besides increasing the dropout is to lower these channels. So this was 128 and now it's just 64. And by epoch 70 we can see 41 and 43, which is a higher loss. So this might not be the optimal architecture, or we just need to train it further. But for the sake of this example, I will stay with a fixed number of epochs, fixed at 100. And we can apply other optimization techniques. For example, our optimizer is Adam. But there's a variation of Adam called Adam W, which also applies weight regularizations. More on that later. So we're almost finished. You can see the loss is not, well, the evaluation loss is almost as good. The gap is small, so that's good. 35 and 40. The gap is smaller. The evaluation loss is a bit higher. I think if we let it run for a few more epochs, then it will be even better than the original. So now let's use Adam W. And our learning rate is a fixed number, which isn't always so great, because as you converge, as the model converges on the error surface to an optimal solution, with a huge learning rate, it cannot fine-tune the model so specifically to arrive at the optimal solution. So if you have a large learning rate, the gradients will either bump too low or too high. So it's like if you were trying to, if you are able to just step 1 meters, but you have to get close, like on a centimeter level. You cannot hit it. So what we do is, with time, we gradually decrease the learning rate. That's one option. There are many options how to change the learning rate as the training progresses. There is like a cosine function that decreases it like this. There are other ways where you just start to decrease it and bump it up again. Just to, for example, to jump out from a local optimum. So what we can do here is, instead of using a fixed learning rate, we can use torch.optim learning rate scheduler, and here you can browse them. There's chained, cosine annealing, that's what I mentioned, exponential LR, linearly decreasing. But what I like, since we have a fixed 100 epochs, is a cosine annealing. D max is the maximum number of epochs. So the drawback of the cosine annealing learning rate is that you have to know in advance how many epochs you will train the model for. So that's not always good. And we need to use the optimizer for that. So write it on the next line. So the start learning rate will be this number. And we have our scheduler. Now we can set eta min, which is the minimum learning rate. It goes down to 0. I'm not sure if we really need that. So eta min, we can set it to 2e minus, let it be maybe this number. And we need to step the learning rate scheduler just as we do with the optimizer. But the optimizer is stepped per batch. And we can step the learning rate scheduler per epoch. And you can try and run your model. It's a good idea to run the model after each variable change, because if you are changing at once too many variables, you won't know what helped and what was counterproductive. But I'm going to change Adam to AdamW. I'm going to add the learning rate scheduler. And one more trick, which will so let's take X and create a tensor with rand-like. Rand-like returns a tensor with the same size as input, just like all the underscore like functions, with random numbers filled between 0 and 1. So rand-like X plus X. So we basically add the noise to the input, and in this way our autoencoder becomes a denoising autoencoder. And because this is random per batch and it goes through many epochs, it will face the same image with a different randomness applied to it many times, at least 100 times. So it will start to learn the necessary features, the key features on the image, even if it sees a noisy one. However, this would be way too much noise, so let's mix these together. Let's say we add 10% noise, or just 7% noise, and we keep 93% of our original image. Let me save this. Was with dropout, the encoder had 0.3, the decoder stayed at 0, and smaller model. And let's run the training again. Another thing we can add, since our learning rate is not fixed anymore, is to print the current learning rate. And you can do that with lr scheduler dot get last LR, which I think will return a list of floats. And I'll restart the training to see how the learning rate changes. Quick note while the training is running, that these hyperparameters, the number of epochs, the learning rate, what learning rate scheduler to use, what loss to use, how many neurons you have where, what dropout percentage to use, etc., etc. Basically, anything you change on the model, some have some scientifically backed explanations, but I read a lot of research papers when they just say, we found that this and that configuration yields better results. So what I gather from this is that basically even the AI researchers, they are just mostly experimenting with this stuff. Maybe not mostly, but even the hyperparameter choices that we now know for sure are a result of decades long of worldwide experimentation. So it's good to do research for yourself, to gather information about how changing one hyperparameter could affect the model. But overall, there are so many, and interactions between them are so many, that you cannot avoid, basically, you cannot avoid experimenting with the hyperparameters and running lots of training loops. So now we are at epoch 70. Learning rate has decreased from that 2 substantially. We have a train loss of 41, an eval loss of 46, 40 and 45. Which will not be the best. But if we end up experimenting too much with hyperparameters and we keep track of what we changed and what the results were, maybe in a more sophisticated form, or just logging, making copies of the model itself and logging the results, then we can just roll back to whatever model worked the best. And of course, we are working in a notebook now, but in real life, you would want to save a checkpoint of your model, not at the end of the training loop, because sometimes the model finds an optimum much earlier, and then it starts to act weirdly. So it's a good practice when you have a loss. You keep track of the min loss. And if the loss is smaller than the min loss after a certain number of epochs, because you don't want to save in the beginning, it doesn't make sense to save the model, like for example, until epoch 60 or 50. But after that, if the minimum loss or the loss is smaller than the minimum loss, then you can save the model and then use that model. However, the training went sideways afterwards. So we have this now. We could leave it running longer, see how it performs, etc. But check our previous runs. This wasn't so great. I mean, the evaluation loss, and it's also your pick. If you are after the best performance, but it's overfitting, but the evaluation loss in our case is the smallest with the largest overfit. This is somewhat better. However, this model is smaller, so it runs faster. So leave a comment, which one would you choose? I'm going to go with this one. So the encoder had a 0.2 dropout, and it was the bigger model. So let's go back, say 0.2, and bump this up. We could even experiment with bumping this to 256. But the overfitting would be even bigger, so then you need to increase the dropout. And it's a whole another round of training, trial and error and experimentation. So running the training once again, I'm going to skip it. So while the last training loop is running, and in that case, it would have been better if I saved the models, because then I would be able to just revert to that. But this is a small example, so let's get back to our cats where we left off. So we have our test data set. We extract an image, turn on model evaluation. We have our latent vector and the reconstructed image. This should pretty much work the same way as before once my training finishes. So now my training finished, and I left the random noise generation in, AdamW, and the learning rate scheduler. The end result is not that great as it was here, because then there was no noise and no, don't need this, and no scheduler. I'm going to go with this model now. I don't want to train it for the 100th time. And let's go to our cat and see what we have with this new model. This is the original guy, this is the reconstructed guy. And this is the guy as the model thinks of it. So basically you can see this image is not so great, but just to demonstrate, we have 128 by 128 by 3 size image, which is 49,000 numbers. And our previous images on Cypher 10 were only 3,000 numbers. And we compressed these into 384 numbers. And we are compressing this into 512 numbers. So, as you probably understand by now, how the autoencoder works is it takes this big image, compresses it down, and then the decoder, it only sees these 500 numbers. It doesn't see the original image. It has no access to the weights in the encoder, the outputs of the encoder, only this 500 numbers. So it almost feels magical that you have almost 50,000 numbers. You can compress it down to 500 and still be able to reconstruct such a blurry but still a great image. And again, you can experiment with setting the latent dimension higher and other parameters to get better results. You probably can. But I leave that up to you. Now for the fun part. Since we have a latent vector like this is a one-dimensional vector. Let's copy this code and since we are going to show multiple images more, let's define a function for this. EM show. img, which will be a tensor. And let's just ensure that we copy it to the CPU before we try to show it. And we have an image. Let's make it image A. Let's make this image B. Pick any random number you want. It's the test data set, so it should be below 1700. Let this be image A as well, and image A rec and ZA. Let's make the same with image B. Show them. So let's show image A reconstructed, image B, and image B reconstructed. So why is that? Because this one needs to be squeezed. Because the first number is the batch number. As you recall, it returns as batch, channels, height, width. So we remove, because the batch will be a 1 prefix here. Okay, we have them. Now, we have two latent vectors learned from these two images. One vector is here in that high dimensional space, and one vector is here. It's a 512 dimensional space, so hard to imagine, but if it was 3D, like imagine like these two vectors or points. What if we sample from this space, but in the middle? So that image doesn't exist. What happens if we take a latent vector in the middle and deconstruct it? Let's try that. So we have, let's say, ZC, and define an alpha. That's 50%. We can take ZA, multiply it with 1 minus alpha, and then add ZB multiplied by alpha. So this is basically ZA plus ZB divided by 2. That's going to be the average. However, this is a linear interpolation, so you can adjust the alpha from 0 to 1, or even further if you decide. And basically you can take these two vectors and you can move along between them. Or in an extraordinary case, try that out if you want, you can go even further. It will not necessarily yield good results, but let's take this ZC and we have the model's decoder actually, and try to decode that ZC to IMGC rec. Check if it works. It does, but we need to show it. Oh, what's this? This guy and this guy mixed together. And if we change it to 0.9, it's going to be at 90% for ZB. So it should be 90% this guy and 10% the other guy. Okay. Let's take this code, copy it into a new code block, and for the fun part, how do we animate this? So we pick our two images, and instead of using a single number to generate a single latent vector, we are going to generate many. And for that, Torch has this function linspace. You can set a start number 0, an end number 1, and steps set it to 25. And just comment out the rest for a bit and print alpha. As you can see, this is a tensor. It's nicely divided between 0 and 1 into 25 steps. But if we try to do this, it's not going to work. So how to make this work? What you can do is take and set alpha. Now print it. And it becomes this shape. It's going to be an array of arrays, and each array contains a single number. So we could say that from a row vector it became a column vector in a way. So now, can we multiply ZC with it? No, because it's not on the same device. One is on my VRAM and the other is on my normal RAM. So here, linspace should have a device parameter, and we declared our device as D previously. And we can multiply. And what will this yield actually? It's too big to print, but if we print the shape, we have 25 latent vectors if we try to print, let's print all the 25, but only the first 10 numbers in it. Let's not print this. So what we can see here, because this is the first 10 number, also this is the first 10 number, and also this is the first 10 number of our latent vectors. So we can see that it is changing. So it's changing basically from ZA to ZB. And if we try to reconstruct it, we can, because our decoder also expects these latent vectors in batches. That's why the original shape of ZA and ZB is not just 512, it is 1 and 512. Now we have 25 images. I don't want to show all here. You can with imshow if you want, but it's long. Instead, import pill the image, and let's generate an array from this. So image from array f to CPU, and we don't have f. F is going to be in frames, because actually these are frames. But remember that all these images are normalized, the RGB values are normalized into between 0 and 1. So first we need to upscale them. And they are floats, so we convert them to bytes. And they are on the GPU, so for each frame, we take that tensor, move it to RAM. Remember, we need to permute the channels because it is stored channel height width, and matplotlib and also below expects it in height width channel format. And now it's nothing machine learning specific. We can save these images. I'm going to save it in my datasets folder. You should save it to some output folder or anywhere you like. So 25 images. If you want a 1 second long GIF or GIF, you would say 1000 millisecond per 25. That would be pretty fast. So let's make it 3 seconds and set it to be looping. Typo here, excuse me. And I'm peeking. Yeah, right, we need to convert to NumPy. And we can test the result. See it here for me. Okay, great, but there's a huge pop in the end because we are interpolating from A to B, but not back from B to A. So in order to do that, to make this animation smooth, let's define a beta that goes back from 1 to 0, also 25 frames, or actually we can bump this up to even anything you like, let's say 60. But we have 3 seconds, so make it 60 frames per second, because the end result will be a 6-second GIF. Let's make it 180 frames. 180 there, 180 back. And so we would need to do the same with beta. And let's change this to phi, and phi will be torch.cat alpha beta along dimension 0. So what this does is alpha now is in the shape (180 and 1). Beta is the same shape. we will concatenate these tensors along dimension 0, so they will become 160 and 1. And so 160 is the size of our batch that goes into the model. So 160 different samples will be decoded. Now, what happens here and why you can just multiply ZA and ZB with phi is because ZA has a shape of 1, 500, and phi has a shape of 360, 1. You can multiply these because PyTorch will broadcast each number here to all of these samples. So basically you have this phi, which is this long, and you have 512 long vectors, and it will just multiply all and broadcast it. But to explain it better, think of it as matrix multiplication. So these are two matrices without getting any deep into PyTorch broadcasting. If these are two matrices, if you multiply them, what will be the end result? The shape will be 160 by 512. So let's uncomment everything, generate, and let's see our output. We can probably bump up the speed. Right, because, yeah, it would be 3000. Because that's how you achieve 60 FPS. Nah, still slow. I leave this to you to tweak around. But that's basically it. You can pick any image. And if you load your own dataset, you can pick any image from those. And what's magical in this is that it doesn't work as like if you were just linearly interpolating between the two images. Because we are linearly interpolating in the latent space, which contains learned feature embeddings. So these vectors in the latent space are organized in a meaningful way according to the data that our model received. So for example, in LLMs, when the text is tokenized, you can represent word vectors. They use a much higher dimensional space, like 12,000, but you can represent, for example, the word man is here, and the network learns that the word woman is like exactly in the opposite direction, like if they were mirrored. or white is next to light gray. So in this latent space, they are organized in a way, clustered in a way that similar meanings are grouped together. I guess this concludes this session. I will upload the notebooks to the Skool community. If you like this video, please click like, subscribe, and join the Skool community. All the material will be there. I am there, and it's free. So thanks for watching, and see you next time.